Describing the vector space of r square, r cube, r to the 4 was easy because it's initially directly represents the cube, the wonderful space that you can imagine. But we have started introducing a subspace within a space that um, um, doesn't necessarily expand to all directions, but look like maybe a plate or a sheet of paper in the three-dimensional space. So we have seen that um, with several descriptions that such subspaces can exist within a space, vector space. But now here comes a new terminology for us to talk about how these subspaces are defined. So remember, in the beginning, a few videos ago, we were questioning what are the set of all points that can be drawn with linear combinations of certain vectors. So that when I was giving this mental exercise, I was actually talking about the word span. So the span of vectors are defined as the linear combinations, all linear combinations of those vectors, and all linear combinations of those vectors uh, makes up a vector space. So we actually talk about what this vector space is all about, like where this um, plane, how this plane is um, populated, or it exists on a larger vector space by talking about the term span. So strictly speaking, the span of vectors v1 all to vn just gives us the vector space that is made up um, by all of these um, that's made up by all of these vectors, right? So let's visit some of the examples from a few videos ago. So like span of 1, 1, 1, which is a vector space on the leftmost, that's going to be on this three-dimensional space, that's going to be only this yellow, you see this yellow line, right? Similarly, if we had two of them, span of 1, 1, 0, 0, 1, 1, it is going to be that plane. And similarly, 1, 0, 0, 0, 1, 0, 0, 0, 1. I'm no longer saying all linear combinations of these points. I'm just saying span of these vectors, right? So similarly, this was going to be a line within a three-dimensional space because the span of these there's only one vector is just a line, and similarly span of these two vectors are going to be a plane in the three-dimensional space, right? So right now so all of the points that we are going to be why this is important, right? All of the points that we will be describing for example on that space, right? So that's a vector space. You know that all of the points, as I walk on that green surface, the points are going to be described with three numbers in our R cube understanding. Like there's X, Y, Z points. But if I know that I am on that space, it is just two-dimensional. Like there's no way that I can fly from that space, right? So that's kind of important because in theory, if I know that I'm on that space, all I need is to describe where I am on that space is two numbers, like how far I go along one direction on that plane versus the other direction. Similarly, look at this space, right? So all of the points as I walk on that line, I need three numbers because I'm like changing my position in the three-dimensional world, but by all of the x, y, and z points are changing. It's actually y is never changing, but it could have changed too. But if I knew that I'm on that line, all I need is how far from the origin that I am. So do you see that this is exactly the same example? Like imagine I'm in a city. I can be. I'm actually going to give that example in a second. I can, if I know that I'm on a road, I, I only need how far on that road I will have to walk, right? So which takes us to the concept of basis. So from span, basis is the other important term. Um, the set of linearly independent vectors that span a vector space is called a basis. Right now, I'm intentionally trying to use this important terminology when I'm introducing things. So again, the same vector space that's a span of 3, 1, 0, 1, 2, 1, that's a vector space. Um, and the basis for that space uh, can be, not necessarily they are, 3, 1, 3, 0, 1 and 1, 2, 1 can be a basis for that space. There can be other bases. You can actually use better bases or different bases for this as long as they are linearly independent. So you can actually have a span of 4 three-dimensional vectors, but obviously one of them, at least one of them, is going to be linearly dependent on others. So the basis is going to be different, right? So if you look at this basis, like 1, 1, 0, negative 1, 1, right? So 1, 1, 1, 1, 1, and negative 1, 1. So like these are two vectors that are orthogonal to each other, that one of them go to like the direction of 45 degrees and the other one goes negative 45 degrees. And so instead of like 1, 0, 0, 1, you can actually make up the R square using this basis, right? So that said, we have a standard basis, right? The standard basis is the x-axis and y-axis that we have been programmed to understand is called the standard basis, but we can have such bases as you see here, different from the standard basis. And the linear combinations of these basis vectors can also make other vectors in that space, right? So the example that I wanted to bring here, we are in Chicago. This is a very fun neighborhood from Chicago, Lincoln Park, Lakeview East. And so we see our Lincoln Avenue here. There's the I guess this is Clark, and let's say our home is here, right? So in the origin, we are Lincoln and Clark, right? And we would like to define these different restaurants, like Elephant Restaurant. There's a dash of salt and pepper, and Cedar Palace. And we can, if we are using the standard basis, we can describe, of course, I made up these numbers. They're not exactly 6 miles west and 6 miles north, but just hang on with me. I'm trying to prove a point. So you say, well, all of these points, all of these restaurants, you can go with 6 miles west and then 6 miles north. Similarly, you can go to dash of salt and pepper. You can go by 4 miles west and 4 miles north, and similarly you can go to Cedar Palace by 5 miles west and 2 miles north. And notice how I am able to describe the positions of these restaurants by two numbers, right? Because I have two directions, west, or I can, like, if I'm going east, then I can use negative numbers, and similarly, if I'm going south, I can use negative numbers. So I am, you can assume that I'm on a number space, right? So imagine if I am on only on Lincoln Avenue, like my data set, my points, the places that I'm interested in, the space that I would like to construct with what I have, even though they can be represented with positions in two numbers, north and west. Um, I can actually represent these data points with how long I am going to move from my home, right? So to go to Elephant's Restaurant, I need to go 6.7 miles on that direction on Lincoln Avenue. So that's what I know. Like I start by introducing my direction, which is my basis, and my points can be constructed using my basis. You see how I'm changing basis right now, like from the standard basis of northwest to east south, and I'm now using a basis, Lincoln Avenue as my basis, right? So like I can then say dash of salt and pepper is 5.2. You see how since I know that they're on a line, I no need to, I no longer need to represent them with two numbers. I just need to know what my basis is. And then I represent all of these data points, my restaurants, with just one number, right? So why is this important? So that's the part that I would like to like take us to very far future. Like we're learning the very basics of linear algebra as it relates to machine learning, but all of these things are for representation learning. In the end of the day, remember the example that we provided with Michael Jordan's image. So there, the data can be represented with several different forms. Like we can have text, we can have images, speech, several different types of data, and we would like all of these data to be represented with a function f in our representation space. That's going to be a vector. So hopefully that vector is not going to be as big as my data, because remember my Michael Jordan image has let's say I take this picture with a 12 megapixel camera, like 3000 4000 3000 rows, 4000 columns, or in the other format, and three channels. So I'm talking about um, millions of data points, right? So I would like to hopefully convert these millions of data points into a vector, because I know, just like my Lincoln Avenue example, even though I can represent them with two numbers or 12 million numbers, I really actually don't need, because I know my restaurants are all on this road. Similarly, my data points are going to be on this subspace, right? The example that I'm giving from far future is this f of the input, this function is going to be nonlinear, but we'll start with the linear, because the moment that you understand the linear representation learning, which we cover in this linear algebra course, um, transition to nonlinear representation learning becomes simpler than it is without it, right? So like after we get to this, then there's another, we can talk about another G function that does your target task, right? So your target task can be classification, regression, detection, whatever, right? So you can, if you go from the image using the subspace, you reduce the data or learn the representation such that you do um, meaningful stuff. You go this one way. One part of deep learning is representation learning, and the other is what we call upstream task, right? And if you go the other way, like if you were to start with a vector, and if you could know the inverse of this f, then you would have Gen AI. But we'll get to that. So like I know um, this is highly nonlinear, but linear understanding is no different, right? So that's how we learn the subspace that corresponds to my data that's actually I'm learning representations, linear representations within this vector space of the data that the data live in, and learning the subspace that my data lives tells me something about the structure of the data set. So that's so in this video we learned the concept of span and basis, right? Spanning, so basis, basis vectors span a space, and from a space, from a vector space, from the input vector, we would, an input vector space, we would like to learn the basis functions, basis vectors can be functions too, basis vectors that span the space, the minimum space, minimum dimensional space that this data sets, data points live, my Lincoln Avenue.